that's what has fueled all the great discoveries. Is that there's first an intuition about something that scientists may not exactly know why they have it, and that's what
Right.
is happening here, and it's worth pursuing.
If there are anomalous phenomena taking place that are outside our general understanding, because we said that's not supposed to happen based on our understanding of physics, and it just seems like it's outside the everyday experience. Could it be that what we're experiencing is something that we normally would not readily observe?
You take the contents of this great piece of material. He changes the velocity in which the electron flows. That's what makes it colder and warmer. Everything is already here. We have to put it together. We still haven't gotten beyond that yet. That's what we're about to do now. We are going to get to the equilibrium of what he's trying to do. I'm Clark Banich, professor of mathematics, and for about 20 to 30 years we've done a lot of simulation and working with a lot of the local companies, NASA, as well as Northrop and Rockwell, and space generation. My favorite field is mathematics, and it is my field of study.
My name is Amar Vakil, and my background is in computational forensics. I've been pursuing that for the last 20 years. I was a former principal investigator at JPL, NASA. There's a research collaboration through what I do. And I have a background. I'm a part-time professor at Southern California Institute of Technology, and I have a bachelor's in electronics technology and associate arts in mathematics. Board certified with the California Board of Professional Engineers and Land Surveyors.
My name is Matthew Polder. Studied math and physics. I was with the Quantum Computing Research Group at UCLA. I did some fundamental publications in that field. Past 20 years have been doing computer programming, computer modeling, been working closely with Paul Laviolette in particular in actually proving some of his hypotheses of particle formation in terms of reaction diffusion systems and modeling them on a computer.
We're here to present an academic preview of John Searle, work on what he has been trying to do for the last, how long it's been, since the 1940s, in an area that is difficult to discuss because it borders on the fringes of science and technology.
There's some kind of ordering principle involved. I mean, that's the direction that I guess is kind of the forefront of the list of hypotheses, I guess, that I'm holding, at the same time being open to anything new. That there is an ordering principle that it is actually an exception to the second law of thermodynamics. And, that's only a statistical law. I mean, I know this is a kind of a crude analogy, but, I mean, you take any statistic, you're going to find systems that can be way outside of the 99.999% of that, especially if you're doing something right, especially if you have a certain information or there's just some kind of new ordering principle that we didn't know before.
Whenever you change the molecular structure of something, it will change. So the molecular structure of some of the particles that we deal with for Searle is changing. Is to us is nothing, but it's a lot to the electrons themselves, because you talk about, you think that when something speeds up, you expect for it to get hotter, or you felt something cooler when you're down in San Diego. The molecular structure has changed, and that's what causes that. And now, when it doesn't have to break as break is, but it has changed, and that's what's happening in there that we don't see, quote unquote, with our naked eyes.
When we look at the law of squares, we can see right away when we look at a magic square as how it could be described. All the rows and all the columns, they all add up to the same number. That itself, when nature is trying to sing to you, and that's kind of what some folks would say, you see these patterns. It's very intriguing for me mathematically to look at it, as Professor Clark mentioned. It's something that, as if nature's pulling on you and said, hey, you got to take a look at this. This is interesting.
Say this is on an object on a plane.
Right.
If I have a force coming this way and a 90-degree force coming this way, and I want to know what is the net force on this object, even though they're at 90 degrees, what I would still do is do a vector addition here to find that then it's going to net go in this direction.
Right. That's the result of the vector.
Yeah. So the question, in that terms, I do this operation on two vectors, which is addition in this case, to get a third vector, and the meaning of that is that is the net force on this object.
Mm-hmm.
So the similar question, when you take two magnetic flux fields,
Yes.
right? You take the cross product. What is the meaning of that? Because we could take any two vectors and do any number of, we could do a tensor inner outer product even or whatnot.
Right.
So that's what I'm wondering. Like, what is the meaning of that operation physically?
I don't know what exactly happening, but I do know that they are crossing each other at 90 degrees. What we're doing is we're getting some kind of a phenomena taking place here. Whether this phenomena is trivial or not, the issue is that what is going on behind it. And all I'm saying is, so again, these two fields are crossing each other at 90 degrees. Wow. Now, I can at least see, I can model that. They have magnitude, they have direction. I said that itself is interesting just to write down. And I do. I write it down. Do I know what the meaning of it is? The answer is no. I don't know what the meaning of it is. I do know that it produces some kind of an effect.
Would this also apply to if I had two magnets and that I put them in a certain position so that, say, the magnetic field, it's like you have the north magnetic field line represented by my fingers, you have another north magnetic field line represented by my fingers.
Mm-hmm.
You put them together and you have them cross at 90 degrees.
Mm-hmm.
Then is that the same situation? I mean, would the two here or?
No, because what's different is here is that you have one of them, which is a stator magnetic field that is radially coming out. So if you were to look at its surface, because it's a flux, magnetic is the intensity times the area cross section of the area. So what you're looking at is a 2 pi radius cross section, and that 2 pi radius, when that thing comes out, it's getting lower intensity as you go further and further out, but it is stronger at the center. And what I'm noticing is that the input of these two fields crossing each other at 90 degrees, at magnitude and direction, and the fact that you're getting an output voltage and an output current, where the current continues to increase and the voltage can remain reasonably constant. In fact, I'd say it remains constant for the sake of argument, causing that resistance, and yet the resistance starts dropping. What it's telling me is that the ratio of the two, the input of those two fields crossing each other and the output, is telling me delta E, delta T. There are two ways of looking at it. And you have a resistor, and then you have a voltage. Just call it V. I'm not, to me, I like both directions. You can look at the whole flow, which is coming down. This is the whole flow. And then, of course, you have the electron flow, which is... So, to me, both of them are useful for different purposes. That's how I see it as an engineer. Sometimes this is more convenient to work with, sometimes this is more convenient. Right now, I'm going to look at it from this end because that's exactly what's moving in Searle's device. So I'm going to look at the electron flow design. So now you can look at this ground as just a reference. It's just a starting point. This is where it's coming. This is where the lower potential is. So there's a pressure for these electrons to bang into each other. They want to collide into each other to send a signal, so that ultimately you're getting a voltage up here. So there's a potential. In Searle's device, if you had a ground like this, there's a problem. You don't have, this resistor generates heat. In Searle's device, no heat. There is something going on here. I put a question mark there. So as an investigator, my job is to do the following. I know this, but I don't know this part here. This is what I don't know. That everything outside this, all this stuff, I'm going to shade here. I don't know this. This is, I don't know. Don't know. I don't understand. This area is unknown. Let me just say unknown. Let me spell that. So this question mark falls out here. But what I do work with is what I can see. What I see in Searle's device, if you have Searle's device is essentially is a set of rings, and then you have rollers, and then you have another set of rings, and then you have another set of rollers. Okay, let's say this is you can keep doing this, but let's say out here you have what they call C coil capacitors. They're C caps that these rollers can pass through. I hope I'm not. It's kind of hard to draw all these things pretty quickly, but I'll just keep it simple. So let's say this is the outer rim. You can look at this just like a standard circuit, except it's different. That's the problem. It doesn't behave the same way. Now, of course, we haven't got to the point where, like I said, this was a phenomenon that Searle had observed. I think it was in the early 40s, and in the 50s, 60s, and also in the 70s. He had experienced this phenomenon. Our job as investigators is to see if this did happen, and if we were to replicate this thing, can we arrive at the same conclusions he arrived at? Can we experience what he experienced? But we're going to do it using some conventional understanding we have here, and then to take it to the next step. There was a famous physicist. He's someone I really admire. His name was Richard Feynman. He was being interviewed at one point, and someone asked Richard Feynman, said, well, how do you feel about all this? And he said, well, one of the things is that when we deal with physics, we sometimes have the answers. We have the mathematics defined, but it sometimes there's more than one solution out there. There might be 15 solutions, and our mathematics tells us, yeah, it's all 15. But sometimes to make that connection between what we're experimenting with and also what our final answers are, we still seem to have to create a scaffolding to go from here to that side. Similarly, in Searle's case, he has some very interesting mathematics. There's a lot of consistency in it. That self-consistency is very enticing for anyone to continue to pursue this. But the problem is there's this big gap between over there and over here, and how to do a scaffolding from here to on that side is almost like doing acrobats. So we almost have to be on the verge of speculation, intelligent speculation. It may not give us all the answers. I might even be wrong about all this. But as far as how I'm going about doing this, but what I'm saying is that if we can look at this, examine this just like a circuit, but we're going to leave this part alone. We're going to look at it like a question mark. Can we assemble a model? Can we assemble a mathematical model that can illustrate what R is? See, here R is equal to V over I in Ohm's law, okay? But here, could R be equal to something similar to that? What we're doing right now is inductively speculating what could be going on. If the phenomena is very unusual, then could it be that also it will require an unusual explanation to the extent that we have to go down to the deeper innards of quantum mechanics to question the idea of what matter really is? Could time itself become part of that process?